Hello everyone, welcome to the course of Digital Signal Processing. Today we will continue our lecture number 12, chapter number 3, that is about Z transform. In previous two lectures of Z transform, we talked about Z transform, relationship with Fourier transform, we talked about the region of convergence, we talked about poles and zeros, we talked about Z plane, we talked about the stability and causality analysis using Z transform. We talked about different kinds of signals. There is right-sided signal, left-sided signal, sum of two exponentials, finite length sequence. In today's lecture, we'll talk about the inverse Z transform using the inspection method, using the partial fraction method, and we will discuss the properties of Z transform. So let's get started. So one of the major role of Z transform is the analysis of discrete time linear systems. So once we do the analysis of discrete time signals or systems, we want to go back into the time domain. So for going back into the time domain, we use inverse Fourier transform. So the inverse Fourier transform is basically related to the region of convergence. So we'll look into the inverse Fourier transform, that how region of convergence plays an important role in order to find out the time domain expression from the Z domain expression using the inverse Z transform. So the typical method that we use is inspection method, partial fraction method, and power series expansion method for inverse Z transform. So in inspection method, we know that if we have a sequence a raised power n u of n, and from this u of n we can see that it is a right-sided sequence and a raised power n represent that it's an exponential sequence. The Z transform of such kind of an expression is 1 divided by 1 minus a Z inverse, and the region of convergence that is associated with this is Z mod greater than a mod. So if we have this expression 1 divided by 1 minus a Z inverse, its inverse Z transform will be a raised power n u of n. So this is the inspection method. For example, if we want to find out the inverse of this x of z, which is equal to 1 divided by 1 minus 1 by 2 z inverse, with the region of convergence z mod greater than 1 by 2. So its inverse will be 1 by 2 power n u of n. So this is the inspection method. Okay, so let's move on to next slide and see this. So here you can see the inverse Z transform of this expression is 1 by 2 raised power n u of n. Because the region of convergence associated with x of z was z mod greater than 1 by 2. But what if we have region of convergence associated with this sequences with this x of z? If x of z is equal to 1 divided by 1 minus 1 by 2 z inverse. If x of z is this and region of convergence is z mod less than 1 by 2, then the inverse Z transform will be minus 1 by 2 raised power n u of minus n minus 1. So you must need to understand that how region of convergence play an important role in finding out the inverse Z transform. So if Z mod is greater than 1 by 2, we have this inverse. If Z mod is less than 1 by 2, we have this inverse. So let's move on to next slide. Now, for example, some sequence has a Z transform of the form x of z is equal to 1 divided by 1 minus 1 by 2, 1 by 4 Z inverse into 1 minus 1 by 2 Z inverse with the region of convergence Z mod greater than 1 by 2. Now, we cannot use inspection method because we only know the Z transform of this term or this term, but we do not know the inverse Z transform of this whole term. So what we can do first for our own is we can plot this. We know that for this single factor we have a pole at 1 by 4 and 1 0, and then we have a pole at 1 by 2 with 1 0. So there are two zeros and two poles. You can simplify this expression in order to find out the roots of numerator and denominator. So here the region of convergence is z mod greater than 1 by 2. It means that both these sequences are right-sided and their intersection appear after 1 by 2. So how we can find out the inverse Z transform of such a fraction? So the simple way of finding the inverse Z transform of such a fraction is by using partial fraction, because partial fraction convert these multiplication into summation. Okay, so let's move on to next slide. So x of z is equal to some constant divided by first factor plus some constant divided by second factor. Now next thing you can do is to multiply this equation x of z with the numerator. Okay, so for example we can multiply x of z with multiplying both sides with 1 minus 1 by 4 z inverse into 1 minus 1 by 2 z inverse. This is equal to a1 into 1 minus 1 by 2 z inverse plus a2 1 minus 1 by 4 z inverse. Okay, this was x of z. Okay, so what we did, we multiply this whole equation with this denominator. Now if I want to find out the value of a1, I can put a2 is equal to 4. If I put a2 is equal to, I need to put the value of z inverse to be 4. If I put z inverse to be 4, this a2 expression gets cancelled and we can find out the value of a1. Likewise, if you want to find out the value of a2, you can put z inverse is equal to 2. So this expression gets cancelled. So you can easily find out the value of a1 and a2. So this x of z is basically this whole expression that you have previously. In the previous slide you can see x of z was equal to 1 divided by 1 minus 1 by 4 z inverse into 1 minus 1 by 2 z inverse. So evaluating this at z is equal to 1 by 4, we can find out a1, and evaluating this at z is equal to 1 by 2, we can find out a2. So anyways, once you get to know the values of a1 and a2, you can substitute these values here, and now we know the inverse Z transform this, because this is from right sided and this is from right sided. The value of a1 is minus 1, the value of a2 is 2. So 2 1 by 2 raised power n u of minus 1 by 4 raised power n u of n. So this, once you reach this point, you can apply inspection method. And on the basis of Z transform you can determine whether it's a right sided or left sided, because our sequence was right sided, as you can see in the region of convergence. So we have u of n and u of n here. Let's move on to next slide. Here we have another example, and you can see we have numerator portion and we have denominator portion. So these are polynomials in Z inverse. So first thing that you need to do is to find out the factors. So the factors of numerators are this and denominator factor are this. From denominator we can see that one pole is at 1 by 2 and other pole is at 1, and the zeros are at minus 1. Both the zeros are at minus 1, and region of convergence is greater than 1. So it means that it is a right sided sequence. Okay, so both this factor and this one is right sided and this one is right sided, so their overlapping occurs after z greater than 1. Now one thing to note, that we cannot apply partial fraction here, because the degree of numerator is equal to degree of denominator. For partial fraction to be applicable, the order or the power of denominator must need to be greater than numerator. So what we can do, we can apply long division. So let's see next slide. So once we apply long division, what happens? We get one factor, we get two second factor, and this is the quotient portion that we get after division. So here we are doing the long division. There is the numerator factor, there is the denominator factor, and we are about to cancel this z raised power minus 2. So the leftover quantity is 5z inverse minus 1 and the quotient is 2. Now we will have x of z is equal to 2 plus 5z inverse minus 1 divided by 1 minus 1 by 2 z inverse into 1 minus z inverse. So we are going to apply partial fraction on this, z inverse minus 1 divided by this. So let's move on to next slide and see this. So now we have to apply partial fraction on this. Just leave this thing out and apply partial fraction on this. We have two factors here, this one and this one, so we have to find out the values of a and a1 and a2. So once we have found the values of a1, that is minus 9, and the value of a2 is 8, we can substitute it back in our equation that was in the previous slide. So this is a1, this is a2, and now we can apply the inverse. So for this constant, the inverse will be 2 delta of n, and for this 9 into 1 by 2 raised power n u of n, for this plus 8 into u of n. So the z transform of inverse z transform of 2 is 2 delta of n. This inverse is 1 by 2 raised power n. This is u of n. So finally we get this form using the linearity property because all of these are getting added. So the one thing that you need to take care is once you apply partial fraction, you must need to make sure that it is a proper form. In proper form, the degree of denominator is greater than the degree of numerator. If it is not, you must need to do long division. Now this is an example of finite length sequence and we want to find out the inverse z transform. So obviously it looks like it's not a rational fraction, but it is a rational fraction. X of z is a rational fraction because we have z square into 1 minus 1 by 2 z inverse, 1 plus z inverse, and 1 minus z inverse. This function has poles at only 0 because if you put z is equal to 0, x of z gets infinity. So this function has poles at z is equal to 0 only. Because this is a finite length sequence, in finite length sequence we do not have any denominator. So we cannot apply partial fraction here. So just solving, like multiplying all these together, we get x of z is equal to this thing. Now we know the inverse of z raised power 2. This is positive. So obviously this is defined at n is equal to minus 2. Minus 1 by 2z, this is defined at minus 1. Inverse z transform of minus 1, this is defined at 0, this is defined at 1 and 0 otherwise. So the inverse of z raised power 2 is delta of n plus 2. For second, the inverse z transform is delta of n plus 1. Likewise for 1, it is delta of n. For 1 by 2 z raised power minus 1, this is z raised power minus 1. So we are just using the property of shifting here and finding out the inverse z transform. Okay, so we cannot apply partial fraction here because this is not in p by q form and the only poles are at 0. When we have pole at other location than 0, then we can apply partial fraction, but here we cannot apply partial fraction. So we can simply multiply them and find out the inverse z transform. Now let's talk about the z transform properties. Number one property of z transform is linearity property. So if I have a sequence x of n and this is scaled by a, and then we have a sequence x2 of n that is scaled by b, then their z transform will be scaled by a and b and there will be addition. So whatever happening in time domain will happen in z domain. The only thing that region of convergence of x1 has to intersect region of convergence of x of 2. So the region of convergence will be overlap region. So there should be intersection between these two z transforms. Now the second property is time shifting property. According to this property, if x of n z transform is x of z, then x of n minus n naught z transform will be just z raised power minus n naught. Okay, so you don't need to find out the z transform of x of n minus n naught. You just have to multiply z raised power minus n naught. So there will be no change in the region of convergence. The region of convergence of x of z will remain same only except for the possible addition or deletion at z is equal to 0 or infinity. Either you will add a pole at z is equal to 0 or z is equal to infinity, or you will delete a pole from 0 or infinity depending upon the n shifting. If the shifting is positive, you are going to delete or add a 0 or pole. Okay, so for example, if I have z raised power minus 1, it means that we are adding a pole at z is equal to 0. But if I have z is equal to z power 1, it means that I'm going to add 0 at 0. Okay, I'm going to add 0 at 0. Let's move on to next slide. So this is just the explanation of this property. Like, we have replaced x of n with x of n minus n naught, and then we say that n minus n naught is equal to m, and then we solve it. We replace x of m here, so n becomes m plus n naught, which we have substituted here. Now because the summation is applied on m, just substituting m starting from minus infinity to infinity, because you have to put n here, so we get the lower limit, and we put infinity and we get the upper limit. So because the limit is on m, so this n naught is a constant quantity, so we can take it this out. So if you see this is a formula for z transform, so x of z. So it means that whenever there is a shifting, the z transform will remain same, only we have to multiply it with z raised power minus n naught, and n naught is basically the shifting. Let's move on to next slide. Now we have a shifted exponential sequence. For example, we have the z transform of the form x of z is equal to 1 divided by z minus 1 by 4 with the region of convergence z mod 1 by 4. Now if I use the inspection method, it is very difficult to understand like what will be the inverse. So why we are unable to find out the inverse? Because this is a shifted function. So what we can do, if I just multiply and divide this with z inverse, I get to have this form. And from this I can see that this is right sided sequence, and if I look at this is kind of an improper fraction, because we have z raised power minus 1 here and z raised power minus 1 here. So what we can do, we can apply long division. So after long division, this is our quotient, this is our remainder, and this is our denominator. So we can find out the inverse. The inverse of minus 4 is minus 4 delta of n. 4 is scaling, and then 1 by 4 raised to n u of n according to the z transform. Now one way is to apply long division. Other way is, I know that x of z is equal to 1 divided by 1 minus 1 by 4 z inverse. Its inverse is 1 by 4 raised to n u of n. And then we have z raised to minus 1. It means that there is a shifting, so there will be n minus 1 and n minus 1 here. So wherever we have n, we have to put n minus 1. So let's move on to next slide and clearly see this. So now we have separated this thing and this delay. So we know the inverse z transform of this is 1 by 4 raised to n u of n. But because of z raised to minus 1, we have to use n minus 1 and n minus 1 here because of the shifting. Okay, so you can use either the long division method or you can use the shifting property. Here we have used the shifting property. I only know the z inverse z of this, but what z inverse is telling, it means that wherever we have n, it must need to be replaced with n minus 1. If we have z raised to power minus 2, then we have to replace n minus 2. Now the other property is multiplication by an exponential sequence. For example, if we have a signal x of n and we multiply it with z naught power n, it means exponential. Then our z transform x of z will be divided by z naught. So whatever the exponential is, our z transform will be divided by that z naught. And ROC will be scaled by z naught. For example, x of n z ROC is Rx, then when exponential multiply, the ROC will be multiplied. Now the notation ROC is equal to Z naught mod Rx denotes the ROC is Rx scaled by Z naught. Okay, so we are basically scaling the region of convergence with Z naught. Now let's clarify this thing with the help of example. So starting with the transform pair, we know that the for z transform of u of n is 1 divided by 1 minus z inverse. Region of convergence is z mod greater than 1. Now we have to find out the z transform of this signal r raised to n cos omega naught n and u of n. We know the z transform of u of n. This whole thing is exponential. Why exponential? Because I can convert this into Euler form. So we know that cos omega naught is equal to 1 by 2 e raised to power j omega naught, and r raised to power n we can take this common, plus 1 by 2 r e raised to power minus j omega naught n. So this is exponential multiplying with u of n. This is exponential multiplying with u of n. So we can use this property. So only thing we have to do is to replace our z with r e raised to power j omega in one case, and in another case e raised to power minus j omega naught. So let's move on to next slide and see how we can do this. So now you see that 1 by 2 is scaling, so 1 by 2 is scaling, and the z transform of this whole thing is 1 minus r e raised to power j omega naught z inverse, because u of n z transform was 1 divided by 1 minus z inverse. So what we did, we just replace z inverse divided by r e raised to power j omega naught. So once you solve this, I get 1 minus 1 divided by 1 minus r e raised to power j omega naught z inverse. And the region of convergence was z mod greater than 1, but now it will be scaled with this r. Okay, likewise for second, our z transform is 1 minus r e raised to power minus j omega naught. So just adding these two, and we will have our z transform. So this is just the simplification, taking the LCM and then solving. The overall region of convergence will be z mod greater than r. So whenever we have a signal and it is multiplied by an exponential, you can use this property to find out the region of convergence and the z transform. Let's move on to next slide. Now this is the differentiation property of x of z. So for example, if we have x of n and its z transform is x of z, but what if we have n multiplied in time domain? So once we have n multiplied in time domain, what we have to do? We have to take the derivative of x of z and multiply it with minus z. So we will have the z transform of nx of n, and its ROC will be Rx. So it means that in differentiation property, the region of convergence remain unchanged. Okay. So if you want to see how we get this expression, then there is a proof here. Starting with the z transform formula, x of z is equal to summation minus infinity to infinity x of n z raised power n. Now taking derivative on both sides, we take the derivative. So the derivative of this summation minus and power comes down, x of n will remain, which is constant, and then z raised power minus and minus 1, because we have taken the derivative with respect to z. Okay, so now multiplying both sides with minus z. So once I multiply both sides with minus z, what happens? We get summation minus this minus gets cancelled with this minus, n x of n, and then z raised power minus n minus 1 plus 1. So this get cancelled. So we left with this z raised power minus n. So we know that if we have n x of n, its z transform will be minus z dx by dz. So from this we get this expression. If any signal is multiplied with the running variable n, then its z transform will be derivative of that z transform into minus z. So let's check an example of this differentiation problem. So for example, we want to find out the inverse z transform of this non-rational fraction. So we can use the differentiation property. For example, if I differentiate it, I get dx by z dz, and log of 1 plus a z inverse will be 1 divided by this argument and then derivative of the argument. So we get this thing, but I need to find out x of n. How I can find x of n? We know that property of differentiation. I have now find out this thing. So next thing will be multiply it with z. So if I multiply it with minus z, I will get a z inverse divided by 1 plus z inverse. Now I have nx of n. I have nx of n, but I need to find out x of n. So what I can do, I can simply divide it with, I find out its inverse. Let's move on to next slide and see. Okay, so we have z dx of z by dz is equal to a z inverse divided by 1 plus a z inverse. We know that the z transform of 1 plus a z inverse is minus a raised power n u of n. Now this is a scaling, so scaling here. Now this z inverse is delay, so we have delay here. We got this expression. Now we have to find out n. We have to find out x of n. So what we can do, we can divide our whole expression by n, and we can simplify this out. So this is how we can use the property of differentiation to find out the inverse z transform from non-rational fraction. So let's see another example of differentiation property. So for example, we have a sequence like x of n is equal to n into a raised power n u of n. Now we know the z transform of this thing, a raised power n u of n, but we don't know the z transform of n into a raised power n u of n. So we know the z transform of this thing is 1 divided by 1 minus a z inverse with region of convergence this. Now in order to compensate this, what we have to do, we have to take the derivative and multiplying it with minus c. So the derivative of this expression gives us this after multiplying it with minus c. Region of convergence remain unchanged, so the z transform of n into a raised power n u of n will be a z inverse divided by 1 minus a z inverse. But a raised power n u of n z transform is 1 divided by 1 minus a z inverse. Once we have n multiplied here, we have a z inverse in this. Okay, why? Because we take the derivative. So that was about the properties, few properties of z transform, in which we talked about the linearity property, we discussed time shifting property, we discussed multiplication by an exponential, and derivative property. In next lecture, we will talk about remaining properties of Z transform. If you have any question, you can ask me in the class. Thank you very much.